seen CNF and DNF conversions, and then started using them for verifying whether a proposition is satisfiable or valid. If the proposition is in CNF, then you can easily find out whether it is valid or not. If it is in DNF, you can similarly find out whether it is satisfiable or not. Then to verify whether a DNF is valid or a CNF is satisfiable, we suggested that we convert it to the other form by using distribution, but that is costly. So, we tried to see whether something can be done about that. It will take some time to do that, do something in that direction, but there are some specific classes or subclasses of these problems which can be solved easily. So, note that this easily means here whether you can solve it in polynomial time or you cannot solve it in polynomial time. The general satisfiability problem as it is, we do not have any algorithm to solve it till now in polynomial time, but if you are told that it is satisfiable, you can verify that within some polynomial time or not. It is not exactly that, it tells that given an interpretation whether it satisfies the CNF, that can be determined in polynomial time. Okay. So, suppose you have a CNF, it has some clauses, disjunctive clauses, and they are all ANDed together. Then you are given with an interpretation, it is told that this interpretation satisfies it. Now, you just want to verify this much, then it should be easy. Is it clear why it is easy? Because in that interpretation you know what are the values of the propositional variables, 0 or 1. So, just look at any clause there, in that clause you just take 1 or zeros, all that you have to see is whether it is giving 1 to any of those clauses or not, then it is satisfiable, right. So, that should be quick. Is it clear? So, it is just something like constructing one row of a truth table. Fine, you have a propositional formula or proposition, you are given with one interpretation, then you are just constructing that row of the truth table. That is, that should take only linear time, 5 polynomial. But the general problem of finding out for all interpretations or searching for an interpretation which will satisfy it looks to be exponential right now, because number of rows in the truth table will be exponential in the number of variables, right, though not exactly in the length of the proposition given or length of the CNF given, but they are related. So, it can be done that way. So, what are the subclasses where this can be done efficiently, right. So, one subclass is suppose you have the satisfiability problem asked for one proposition which is in CNF, and in the CNF there is only one clause, one literal in every clause, right. So, basically it is a conjunctive clause. Is it clear? It is a CNF where each disjunctive clause contains only one literal, right, one occurrence of a literal even. The literal can be different in each clause, right. For example, let us give one, so it looks like P1, this itself is a disjunctive clause, there is only one literal in a clause. Similarly, there is another clause which can be say not P1 or even not P2, let us say. Okay. There is another clause again having one literal, and so on. It looks only that way. There is only one literal in each clause, not necessarily the same literal. Fine. Still, the thing should be easier here to handle, whether this is satisfiable or not. Right. See, the thing is, if P1 is there, not P1 should not occur, then it is satisfiable. That is, the same thing should be true for all the literals coming up there, and that should be easy. So, this is a subclass, but these formulas or these propositions are called to be in one CNF. in each class there are at most one number of literals present. So, there is no disjunction in any of these clauses here, right. So, this is a one CNF. Similarly, you can have a 2 CNF. So, which will say that each clause in this CNF will have at most 2 literals. So, there can be at most one conjunction there, right, one disjunction there. For example, you take say P1 or P2 and P1 or P3. This is an example of a 2 CNF. There can be only one also. For example, I can have this also. This is again a 2 CNF. Is that clear? So, similarly, you can define a K CNF, where each clause there will have at most K minus 1 disjunctions, K literals, yes, occurrence of literals is at most K, fine. So, in this case we say that the corresponding problem, satisfiability problem, is again coming with that number. We say whether given a K CNF determine it is satisfiable or not. You say you are solving K SAT, right. So, if the general satisfiability problem is SAT, we will write that as K SAT. Is it clear? So, K SAT will be the problem whether given any K CNF it is satisfiable or not, that is the K SAT. Now, we have an efficient algorithm for one SAT. You can determine any given one CNF whether it is satisfiable or not. Similarly, we have an algorithm which is also efficient for 2 SAT. If there are only 2 maximum of 2 literals present in each clause, then you can solve it easily. So, there is completely one logical algorithm, but there is a graph algorithm which is easy to visualize. They are equivalent. What it says is for the 2 SAT, it bases on a simple observation. In a 2 SAT, a clause will look something like this, okay, where P1, P4 are literals, not necessarily propositional variables. There can be negation symbols. Okay. So, this you can write equivalently as not P1 implies P4, okay, because of double negation and implication rule. Is it clear? P implies Q is not P or Q, or you could have also written as not P4 implies P1, right. This is commutative, but implies is not. So, we need both of them. You can write this way or you can write this way. Okay. Now, what we do, given any 2 CNF, we will construct a graph from this. So, constructing the graph is simple. You look at a clause, for that clause you will have either this way or this way, in fact both of them, right. So, for the clause P1 or P4, now what you do, take a node which is P1, let us label it as P1, take a node which is labeled as P4, take similarly 2 other nodes which are labeled as not P1 and not P4. Okay. So, once P1 or P4 is there, you have not P1 implies P4. So, from not P1 to P4 have one directed edge that represents your implies, fine. Similarly, not P4 implies P1, you have another directed edge. Okay. So, what you do, what the procedure is asking you to do, given a 2 CNF, first find out what are the literals coming there or what are the propositional variables. Say propositional variables are P1 to Pm, then you introduce 2m number of nodes, their labels will be P1 to Pm, another set of those other m will be labeled as not P1, not P2 up to not Pm, fine. Then if P1 or P4 is a clause, then have these 2 edges in that graph. Now, construct the graph. So, once the graph construction is over, this one will be unsatisfiable if and only if there is one path from some literal p to its negation, and automatically there will be another from not of p to p also. So, you have to go for a cycle, right, p to not p to p again. So, in this graph what we see is, suppose you get a cycle from some p to p itself, but coming via not p, right, then the original 2CNF is unsatisfiable, and conversely this can be proved. So, it is just a graph search problem for the cycles, but coming to 3-SAT there is problem. Till now we have not discovered any algorithm which will solve a 3-SAT instance in polynomial time, in arbitrary 3-SAT instance, right. The reason is, if you do that, then SAT itself will be solved. You can solve 3-SAT in polynomial time, then SAT can be solved in polynomial time. There is a reduction, right. So, you need not go for 4-SAT verifying. If you want to solve this problem, just concentrate on 3-SAT, that is what it says. This is surprising, because the subclass itself is as powerful as the whole class, that is what it is going to say us with respect to this searching for an efficient algorithm. So, what it says is 3-SAT, there is a reduction from SAT to 3-SAT, right. So, an algorithm for solving 3-SAT can be used to solve SAT itself, whether that is satisfiable or not, only for the satisfiability determination we are concerned with that only. Then need not be equivalent. Suppose I have this P or Q or R or S, again I look at a class. Can I write this class, or corresponding to this class can I have another 3CNF, let us say, where I can show that this is satisfiable if and only if the target 3CNF is also satisfiable. This is what I want, not exactly equivalence, right, only satisfiability is to be preserved, that is our aim now. So, what I do, say I take P or Q or another, say Z1, this I construct, I just or it. Next I write and R or S or not Z1. Suppose I introduce this way. Okay. Now, question is, suppose I write as C and write this as C prime. Can we show that C is satisfiable if and only if C prime is satisfiable? Well, we can do that, provided we try to prove it. Let us try to prove. Let us take this as a conjecture and try to prove. If you are through, okay, we will try for the next one, we will generalize. If not, then we have got a counter example and stop it there, right, leave with our unhappiness. So, let us see what happens. Suppose this is satisfiable. Okay. So, that means at least one of them is 1, others can be 0, allowed to be 0, all of them can also be 1. So, at least one of them is 1. Suppose P is 1, right. So, this is 1, then this whole clause is 1. Okay. What about this? If it is 1, I am through, right. So, suppose it is 0, when can it be 0? When R is 0, when S is 0, when not Z1 is 0, but not Z1 I have freedom, it has not been fixed by my interpretation, it is a new propositional variable. So, question is, can I extend the interpretation which satisfies C to another, giving new values for these new propositional variables which will satisfy it, fine. That we can do here. I can take not Z1 to be 1 by taking Z1 as 0. If I take Z1 0, it is still 1 and this also becomes 1. So, it is possible.
Satisfiable for certain values, for certain interpretation of PQRS, And so, such that for the same interpretation of PQRS, the initial proposition is also satisfiable.
See, there is some gap there. I want to prove C is satisfiable if and only if C prime is satisfiable. So, suppose I try the first one, if C is satisfiable then C prime is satisfiable. For that itself, what I start with a model of C, right. Now, what I do, I want to find one model of C prime. It may not have any connection with that model in the abstract case, right. But usually what should I do? I should try to see whether I can modify the given model to make a model for this, right. In fact, the theorem does not ask you, or the result does not ask you to take that model and then find a model for this, no, but that is a hint for us for the proof, fine, any model can do for this. Now, what I do, our procedure told us that I can start with that model itself and assign Z1 in such a way along with that. So, it is an extension of that model, so that it will be a model for C prime, that is all. Is it clear?
Obviously, use the model that you used for the previous one, right?
Right.
They are using the satisfiability condition of the previous one and then saying this has to be satisfied
Right.
if that follows.
Yeah, so that is one part. See, we have to prove both the things. If C is satisfiable, then C prime is satisfiable. That is our first. Second thing, if C prime is satisfiable, then C is satisfiable. Now, for the first one itself, if C is satisfiable, it has a model. So, I start a model of that. Now, I have to construct a model for C prime. It might come from that model, it might not come, does not matter, but since it is there, let me use it. So, I see that I can extend that model to include a valuation for Z1 for the new variable, which will be a model for C prime. Is that right? So, it looks viable in that case. What about the converse? Suppose C prime is satisfiable. So, that means both of these are assigned to 1, okay. P is 1, Q is 1, Z1 is 1, R is 1, S is 1, not Z1 is 1 in the same interpretation. Yes, not possible, but when you take a model of this, it says this clause is evaluated to 1, this clause is evaluated to 1. It does not mean all the variables are to be assigned to 1 here, it is an OR statement, right. So, the whole is assigned to 1, which says P is at least one of this, P Q Z1 is 1, right. So, this says at least one of this is evaluated to 1, right, that is only given. So, from this I choose P to be 1, that itself finishes. Okay, let us see, suppose C is P or Q or R or S or T. Okay. For this part we know our C prime will have P or Q or Z1 and R or S or not Z1. Now, you have to take care of this T. Okay. This is up to this, yes, I have to take care of this T. So, what I do, I have Z1 here, I have not Z1 there. Okay. So, let me take say T or not Z1 or Z2, I make it Z2. Okay. See, this Z1 and not Z1, that helped us, right. So, I do not want to leave that pattern, I want to keep it. So, I have P or Q or Z1, then I take T or not Z1 or Z2 and then R or S or not Z2 as earlier. So, in this ordering as it is written, I am considering this way. Fine. So, first part let us see only, second part should be through, it should be quick, right. So, first part, if this is satisfiable, there is a model for this, how to construct this, how to give values to Z1, Z2 and so on, it is an extension. So, if P is 1, I keep it as it is, Z 1 I have freedom to choose later, right, and I come to this. If T is 1, similarly I have freedom to choose Z 1 Z 2 later. If T is 0, then I have to choose one of this. Okay. So, I become greedy, I take Z 1 to be 0 here, right, because it is not required, P is enough to satisfy it. So, then let me take Z 1 0. Then what happens here? Not Z 1 becomes 1 automatically, our construction will go like that, right. So, automatically this one will become 1, but Z 1 is 0 and Z 1 does not occur here. So, out of R or S they can be false, we are considering the worst way when it can be breaking down. So, if R or S is 0, I have still freedom to choose not Z 2. So, not Z 2 I choose to be 1, so Z 2 is 0 here. Is it okay? So, this can be done, it looks. So, how does it look in general? Suppose my C is equal to, let us take that first case, P or Q or, so I say P 1, P 2 or P 3 or P 4. In that case, I write C prime equal to P 1 or P 2 or Z 1, and we wrote or Z 1 or not Z 1 or Z 1. Okay. So, next we take P 3 or P 4 or not Z 1. Okay. Now, suppose C equal to P 1 or P 2 or P m, where m is greater than or equal to 5. Fine. Then only that inside pattern is coming, otherwise for 4 case it is quick. Then we write C prime equal to P 1 or P 2 or Z 1, and let us say go next P 3 or not Z 1 or Z 2. Okay. It continues, the same pattern continues till somewhere. After that we will come last to P m minus 1 or P m or Z m minus 2. Looking at this is the last term, right. So, if this is my m minus 1, this should be 2 less, m minus 3, then it should be 3. Okay. M minus 3, not of that, yes. And what will be here before it? Look at the case 5, yeah, P m minus 2 or not of Z, before it m minus 4 or Z m minus 3. That is our proposed construction. Okay. Now, we should be able to prove that C is satisfiable if and only if C prime is satisfiable. So, let us try. So, we have this, C is satisfiable if and only if C prime is. Now, where should we start? First part, suppose C is satisfiable. Suppose I is a model of C. So, that means I is giving some values to P 1, P 2, P m, right, some values. So, that the whole thing is evaluated as 1. So, that means at least one of P 1 to P m is 1, that much we know. others we do not know. Okay. Now, just look at our proof what we did here for the case for 5. Suppose q is 1, p is 0. How are you going to do it? This is 1, this is 0. Okay, p is 1, that is the first case we had taken, remember. P is 1, so this one we do not have to worry at all. Now, what about this? So, we choose this to be 0, so that not z1 can become 1, forgetting about t values, right. So, in case of p to be 1, we have chosen z1 to be 0. Okay. Next, this becomes 1. Now, z2 can be chosen to be 0, so that the other one becomes 1, right. So, z2 also we have chosen as 0. Okay. That itself does. We do not have to worry about what the other things are given, q, r, t, s, we do not have to worry. Looking at p alone, suppose p is 0, say q is 1. Now, how are we going? So, we start from q itself, forget p, we do not have to worry. Q is 1, so since this is 1, well, I take this to be 0 associated with it, whatever that variable is, same thing does, same thing holds. Suppose instead of q is 1, I have t is 1, q is 0. Now, I have to satisfy this first. So, z1 I have to take 1, there is no option now, right. So, then t comes here, and z1 is fixed, then that onwards the other scheme works, z2 is 0 as it is, there is no problem. Do you see the pattern? If p is 0, but q is 1, then I have to take z1 as 0 from q onwards. That is, if a variable p2 is 0, p1 is 0, then I choose z1 to be 0, and then take z2 to be 0, z3 to be 0. Now, all z's I just take 0, whatever earlier model that works, right. If t is 1, that is p3 is 1, so that is up to p2, let us say they are all zeros, then what I do? I have to take z1 as 1, all the others are zeros. Now, can you tell me the scheme?
Literal is true, that many minus 2 number of ones and then remaining zeros.
Yeah, suppose I call this as k, right. Before that all of them are zeros, but pk is 1, right. Then what I do? I take zk minus 2 as 1, okay, till that. So, before that say z1, z2 up to zk minus 2, that I take as 1, all the others are zeros, that should work, right. So, let us see how to write it. Suppose I is a model of C. In this model, let k be the least index such that what happens? Pk is 1, all others before it are 0, okay, such that Pk of I is 1. So, once we say least index, it means before that all of them are 0, right. Is the least index such that I assigns it to 1. So, that means I assigns all the variables before it to 0. Is that okay? If not clear, write it. Note I of p1, I of pk minus 1 are 0, that is what it says, because it is the least index, and all the others we are not bothered. Now, what we do? Extend I to or for z1 to m minus 3, m minus 1, okay. Up to m minus 1 we are involved, p m, then z m minus 3, z m minus 4. So, up to z m minus 3, z 1 to z m minus 3 by what to do? Yeah. Suppose it is the kth one, then we want to put up to k minus 2 as 0, all the others are 1. Is that okay? Sorry, up to that 1 and 0 onwards, 0 after that. So, we say I of z 1 equal to I of z k minus 2 as 1 and I of z k minus 1 to I of z m minus 3 as 0. This is our new interpretation I. Though we are writing the same I for both the things, it is an extension, it is a new interpretation. It has now in its domain z 1 variables, which were not earlier. In that way it is different, but it is an extension, it keeps the same values to p k as earlier. Okay. Now, we should say that I is a model of C prime. It is only construction, it is a guesswork only up to some 5, we have to really show it, fine. So, our claim is now I is a model of C prime, this C prime. Now, let us find out how it is a model of C prime. Now, for the first class what happens? I of this up to
z k minus 2 we
k minus
all
2.
one.
So,
After
first k minus 2 clauses are evaluated to 1, right. So, now I is a model of first k minus 1 clauses. So, when we wrote C prime that way, we are not going to rewrite it, we have to write it that way only. So, that first second they are meaningful. Okay. How many are there? You are giving 1 as k minus 2. So, you have to say k minus 2 clauses due to first condition. Let us say the first condition as 1, second condition as 2. So, due to 1. Next. So, we have to be concerned about k minus first class and onwards. So, k minus first class has what? P k. So, p k is assigned to 1. Now, due to 2 other clauses are assigned to 1 by I, right. Hence, I is a model of C prime. So, that is the difficult part, you have finished. So, now the converse part. Conversely, suppose I is a as a j is a model of C prime. Now, we must find a model for C. Okay. So, what to do here? Yes.
There will always be one. There will always be one clause. There will always be one clause, such as there where between the k minus 1th clause, wherein all the z's will not contribute to the clause that being validated, and it is because of the literal over there. Hence, since we can always find such a clause, therefore the initial C is satisfiable.
So, idea is, if you look at the z's, you have one z 1, then there its negation. Okay. If you look at all z m minus 3, then also it is negation. So, suppose you have a model for C prime, it will assign z's to something 1 or 0, whatever it is. Okay. So, whenever one is assigned 1, the other is assigned 0, fine, in the same model. Therefore, in this class, suppose you have not z m minus 3 is assigned to 0, then one of these will become 1. We have to proceed similarly. This similarly is difficult to write. Okay. So, how to write it exactly?
You can show that Z1 and not Z1 or Z2 and all that dot 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 is unsatisfiable.
You want to prove by contradiction. So, in that case we assume that I is a model of C prime, but I is not a model of C, or there is no model of C rather, right, not that the same I or same J, there is no model of C. Okay. This is what you want to say, is it not?
Remove all the literals from the previous all the P1s, all the PIs will remove from the C dash. So, we will have a new construction that is Z1 and not Z1 or Z2. We can show that it is unsatisfiable. So, from that we can show that C dash will be satisfiable only if one of those other literals is 1, then C will be satisfiable.
So, removing means assigning them to 0, is it not? That is what you are telling. So, better assign them to 0, that will be explicit. So, that is same thing as assuming C is unsatisfiable. Now, let us try that. Okay. So, suppose J is a model of C prime, but C is unsatisfiable. So, once C is unsatisfiable, whatever model you choose, whatever interpretation you choose, it is not a model of C, right. Therefore, J is not a model of C prime. The same J is not a model of C prime, model of C, right. It is not a model of C. Okay. So, which means J assigns 0 to all those variables. So, that means J of P1 equal to J of Pm equal to 0. Okay. Now, look at our construction, all these are zeros everywhere up to this, all these are zeros, but C prime is satisfiable. So, starting from the first class we have to take J of Z1 as 1, is that right. So, once J of Z1 is 1 in the second class, P3 is 0, not Z1 is 0, therefore, Z2 has to be 1. See our construction of list K, it is really helping us now also. So, the same pattern is coming here. So, that means you will see that all of this Z1 to all of this Zm(3) has to be 1. If they are 1, then the last class becomes 0. Therefore, J is not a model of C prime, which is a contradiction. Is it clear? So, let us write it. Then the first class in C prime has P1, P2, Z1. It says J of Z1 is 1. Okay. Now, from the second class we see J of Z2 is 1, right. So, continuing up to the last but one class in C prime, we see that j of z1 equal to j of z2 equal to j of z, what is that, m minus 2, m minus 3, z m minus 3 is 1. Then j of the last class, okay, which is j of p m minus 1 or p m or not of z m minus 3 is 0. Okay. So, this contradicts the assumption that J is a model of C prime, is that right? So, that means we have shown that C is satisfiable if and only if C prime is satisfiable. Okay. C prime is a CNF. So, that means a clause is satisfiable having m number of literals if and only if a 3 CNF is satisfiable, and we had given the construction for the 3 CNF. Now, if you start with any CNF, each clause you can write as a 3 CNF corresponding primes. Okay. Then go on conjuncting them together. So, you end up with a 3 CNF. Now, the question is, will this 3 CNF have exponential length corresponding to the length of the original CNF? Let us look at a clause. For each clause, how many clauses you are giving in the 3 CNF? Suppose C has m literals. So, in C prime at most 3 m occurrences of literals, each one is 3. So, at most there are m factors, really less, right, it will be less. So, let us write at most 3 m occurrences of literals. Okay. So, that means length of this and length of this is just a constant multiple. Okay. Length means total number of symbols occurring in it. So, length of C prime is a constant multiple of length of C, and this constant is fixed for any given clause, it does not matter whatever it is, right. Why? Because you take any, start from any given CNF. In the CNF, first find out what is the maximum number of literals occurring in a clause, right. So, this constant will depend on that. So, for the given C, you can find one constant here 3, 4 or whatever, right. So, that constant remains for all, it does not change throughout when you write for clauses to 3 CNF, fine, you take the maximum possible. So, since it is a constant, now if set can be solved for this efficiently, set can be solved for this efficiently. Okay, it is just a constant multiple, length is not making it exponential times the length of that, it is just a constant multiple. Is it clear? So, therefore, set can be converted to 3 set. If you solve only 3 set, that will solve your NP problem, because set is NP complete, 3 set is also NP complete. So, if you can solve or prove that 3 set is in P, then that will show NP equal to P. If you show 3 set is not in P, yeah, that will solve P is not equal to NP or not? Yes, because and completeness is required there, right. It is not only, it is completeness. So, because set is NP complete, so 3 set is also NP complete. So, it belongs to P or not in P determines whether P is equal to NP or P is not equal to NP. Okay. Fine. So, let us stop here. Today only we have done this much, that set or 3 set, they are equivalent in this sense. Okay. 3 set, if it is proved to be in P or NP, that way P and NP their fate also will be decided.